Okay, the last part of these notes revisits this idea that we talked about at the end of section 9.1, which is what a type 1 error is and what a type 2 error is. And we had mentioned earlier that a type 1 error is any time that you are rejecting a null hypothesis when, oops, that null hypothesis was actually true. Okay? And what you're going to need to be familiar with on the AP test is the probability of committing a type 1 error is whatever the alpha level is set at, okay? Whatever your significance level is, okay? So for example, at a significance level of 0.05, that means that you have a 5% chance that you are going to reject a null hypothesis when the null hypothesis was in fact true. Okay? So that's kind of easy to know that whatever your alpha level is, that's really the odds of you committing a type 1 error. Okay? So if you want to keep your type 1 error odds low, then you should set your alpha level low. Okay? But a type 2 error, and a lot of times we refer to that as 2Fs, is just a helpful way of remembering this. A type 2 error is anytime you fail to reject a null hypothesis, but that null hypothesis was really false, meaning we should be rejecting it and we're failing to reject it. Okay? Now, the probability of a type 2 error is known as beta. Okay? So there's a beta percent probability that you are going to fail to reject a null hypothesis when, oops, that null hypothesis was really false. Okay? You are not going to have to concern yourself or worry about how you get beta. By the way, if alpha is 5%, that does not mean that beta is 95%. Okay? In fact, it's really the confidence interval that's linked more to 1 minus alpha. If you're setting a significance level at 5% and you were going to do like a similar confidence interval for that particular problem, that's like being 95% confident in the interval that you've created would capture the whatever the parameter in question is. Okay? What we want to spend our time looking at here today, though, is this idea of power. And we didn't actually address this in the last notes, but this is something that it has a heavy emphasis in AP Stats. And power is linked very closely to a type 2 error. Power, and this is what you want to keep in mind, power is a good thing, okay? So when we talk about, wanting to increase the power or calculate the power, what power is it is when you correctly reject a false null hypothesis. So think about it. If the null hypothesis is false, then we would want to reject it, okay? So what power is power is us avoiding a type 2 error. And the probability of avoiding a type 2 error is 1 minus beta, because if beta is the probability of making a type 2 error, obviously 1 minus beta would be the probability of not making a type 2 error. Okay? So power is avoiding a type 2 error. And the best way to because it kind of flows off the tongue sort of nicely, is to remember this phrase, correctly rejecting a null hypothesis that was false. To correctly reject, okay? So there's a 1 minus beta, there's a 1 minus beta percent probability that you will correctly reject a false null hypothesis, okay? So power is the probability that you are not making a type 2 error, and of course, the higher the power, the less likely the mistake, okay? So there's this chart down here. I'm not going to spend a lot of time on it, but I do just want to mention a little bit of a typo that's down here. I fixed it right here in purple. The probability of making, this should say a type 2 error is beta, And then this right here should say 1 minus beta is the power of a test. Okay, and you're welcome to kind of look at this chart. It kind of provides a graphic way of sort of organizing this whole idea of a type 1 error, type 2 error. But the idea is you just want to keep in mind that power is a good thing, and it is correctly rejecting a false null hypothesis. So if we think back to the potato chip example, where the null hypothesis was that the proportion of blemished potato chips was 8% versus an alternative that if it's more than 8, they send the shipment back. Okay, now our conclusion on that example, if you were to flip back and look at that example in your notes, the conclusion we made was we failed to reject that null hypothesis, okay, the one where we're saying the amount of blemished potatoes is 8% rather, okay. If the true proportion of blemished potatoes in the shipment, though, was really 0.09, then the null hypothesis would really have been false. And that means that we would have made a type 2 error because we failed to reject a null hypothesis that was false. Okay? Now, this is just an if. You know, we're just saying hypothetically, if the true proportion of blemished potatoes was 0.09, then we would have made a type 2 error. Okay? Now, we also would have made a type 2 error if the true proportion of blemished potatoes was 0.11 or 0.15. Okay? Anything greater than 0.08, if that was really the true population proportion, would have resulted in a type 2 error, okay? Because once again, remember, the conclusion we made is, if you look back at that example, we chose to fail to reject that, okay? Now, the reason I'm looking at all these hypotheticals, like what if it was 0.09, 0.11, 0.15, is when we talk about the probability of making a type 2 error, it depends on a lot of factors. One of those factors is if the true proportion, in this case of blemished potatoes, is farther away from the hypothesized value. Remember, the hypothesized value is technically the 0.08, and we're saying, well, what if the true proportion was 0.09, 0.11, 0.05? Okay, the farther away the true proportion is from the hypothesized, we call that the effect size. And so the more likely you would discover that that null hypothesis was actually false. And we may have correctly rejected that false null hypothesis if the hypothesized value is much more distant from the true population proportion. Now, we don't know what the true population proportion is in problems. If we knew that, we wouldn't even need to be doing a significance test because we would know what that value is. Okay? But it's just this idea here of the farther away the true population proportion is from whatever the null hypothesis is, it makes it easier to detect that, and it decreases the chances of us making a type 2 error. Okay, which means we're increasing the power. Okay, so I want to talk about 3 things that really would increase power. And I see this a lot in multiple choice questions where they're wanting you to try to figure out what are some factors that you could do to increase the power of a significance test. And this one is kind of obvious, but one thing that you could always do is you could always increase your sample size, okay? And the idea behind this is the more data that you're using, the better information you have, okay? So the larger the sample size, the higher the power of the test. That means you are increasing the likelihood that you are going to avoid a type 2 error, which in turn increases power, okay? The second thing that you could do to increase power is you could increase the significance level, okay, which is what alpha is, okay? Because as alpha goes up, that means the probability of a type 1 error goes up. If the probability of a type 1 error goes up, that causes the probability of a type 2 error to go down. And if the probability of your type 2 error is going down, that is making your power go up. That's what power is. It's avoiding a type 2 error. Okay? So if you were to increase your alpha level from 0.01 to 0.10, that would increase your power. Okay? So the trade-off is, it also is increasing the odds of you making a type 1 error, but it's decreasing the odds of a type 2 error. Okay? For example here, it says, if you were to choose an alpha level of 0.10, okay, that means that you are totally fine with rejecting a true null hypothesis 10% of the time. And what that's going to do is, that means that you're more likely to reject a false null hypothesis, okay, which will increase your power. Okay? Same can be said here. If you changed it to 0.01, you would be very careful to avoid rejecting a true null hypothesis. Okay, so it makes it a lot harder to detect that. Okay, this little chart underneath here just kind of summarizes these three ideas. Okay, that the last thing, I guess I didn't touch on this, is the value of your alternative parameter. That means where the true parameter lies compared to your hypothesized parameter. The bigger distance those two things are apart, like the potato chip example, the more likely you would be able to avoid a type 2 error, and therefore it would increase your power. Okay? Now, the problem with this is we don't really have control over that because we don't really know where the true parameter lies. And so we can't really play with the distance between those two things when we don't really know where the true parameter is. Okay? So these are the three factors in this little chart here that are affecting how you could increase your power. Okay? The first one is for you to increase the effect size. Okay? Obviously this increases power. It's going to decrease the probability of a type 2 error, but this is really unrealistic because it says you don't know the effect size in reality. That's the distance between your hypothesized value and the true population parameter, so you don't really have control over this. So that one is not entirely realistic. Okay, but these other two you could do in the design of your study. Okay, you could increase your sample size. The trade-off is this is going to cost time and money, but this is generally the best way for you to increase power of a test. And the other thing is to increase alpha, your significance level. Okay, and the cost that you pay for this is, when you increase the significance level, it does increase the likelihood of you committing a type 1 error, okay? And that's usually more serious than committing a type 2 error, okay?